On October 17, 2025, at 0314 UTC, the Atlas telescope array in Hawaii detected an anomalous signal emanating from the interstellar object designated 3I Atlas, a body first cataloged during its unexpected transit through the outer solar system. Operated by the University of Hawaii's Institute for Astronomy, Atlas is designed to scan the sky for near-Earth objects and transient phenomena, its wide-field cameras capturing data across multiple wavelengths. The detection was initially routine, flagged by automated algorithms trained to identify deviations in celestial motion or luminosity. Within hours, observatories in Chile and Australia corroborated the signal, confirming its origin as 3I Atlas, approximately 2.7 astronomical units from Earth. This object, roughly 300 meters in diameter, had been under scrutiny since its discovery 3 months prior, its hyperbolic trajectory marking it as an interstellar visitor unbound by the sun's gravity. The global astronomical community, coordinated through the International Astronomical Union, prioritized tracking to assess its composition and behavior. The signal's characteristics were immediately archived in secure databases, accessible only to cleared researchers under NASA's oversight. Atlas employs photometry and spectroscopy to analyze light curves and chemical signatures, methods that have reliably mapped comets and asteroids for decades. Initial data indicated 3I Atlas emitted faint, periodic pulses in the infrared spectrum occurring at intervals of 47.3 seconds. These pulses were consistent across multiple observation platforms, ruling out instrumental error. The object's albedo, reflectivity, and thermal emissions aligned with known interstellar bodies like 1I Oumuamua, yet its signal periodicity suggested an organized structure, a feature absent in natural phenomena. NASA's Jet Propulsion Laboratory, tasked with trajectory analysis, confirmed the object's path would carry it beyond the ecliptic plane, reducing chances of gravitational interference. By October 18th, the signal's consistency was undeniable, yet its implications defied explanation. The pulses carried no decipherable information, but their precision mirrored artificial constructs, not random cosmic noise. Then, at 2241 UTC, the signal ceased abruptly across all monitoring stations, leaving a void in the data stream. Subsequent scans detected no trace of 3I Atlas's infrared signature, despite its predicted position remaining within observational range. This sudden silence, unaccounted for by any known astrophysical model, marked the boundary where verified observation met uncharted uncertainty. The anomaly manifested in the data as a precise and abrupt cessation of the infrared pulses from 3I Atlas, occurring simultaneously across independent observation networks. Standard astrophysical models predict that interstellar objects composed primarily of ice, rock, or metallic compounds exhibit gradual variations in emission due to rotational dynamics or outgassing as they interact with solar radiation. In contrast, the recorded deviation showed the signal terminating mid-cycle, with no detectable decay or residual thermal glow, as if the source had been extinguished instantaneously. Spectroscopic analysis from the Very Large Telescope in Chile confirmed that prior to the cutoff, the pulses maintained a frequency stability better than 1 part in a million, a level of coherence typically associated with engineered systems rather than natural cosmic processes. This stability persisted for over 19 hours of continuous monitoring, only to vanish without precursor indicators such as spectral broadening or amplitude fluctuation. Radar echoes from the Arecibo Observatory's successor facility in Puerto Rico, aimed at verifying the object's physical presence, return null results post-silence, despite orbital projections placing 3I Atlas well within detection limits. The absence of debris trails or fragmentation signatures further compounded the irregularity, as any natural disruption, such as a collision or sublimation event, would leave measurable aftermath in the form of scattered particulates or altered albedo. Several interpretations have emerged within the scientific community to account for this behavior, each grounded in observable data yet leaving critical gaps unresolved. One perspective, advanced by researchers at the SETI Institute, posits that the pulses could represent a form of modulated emission from an artificial probe, where the sudden halt indicates a deliberate shutdown protocol, perhaps triggered by detection awareness. This view draws on the object's hyperbolic velocity, exceeding 40 kilometers per second, which aligns with interstellar travel efficiencies, but it falters in explaining the lack of subsequent reactivation or directional beaming toward Earth. Alternatively, astronomers at the European Space Agency propose a natural explanation involving exotic matter phases, suggesting 3I Atlas might harbor cryogenic ices that undergo rapid quantum tunneling under specific thermal thresholds, leading to an implosive collapse of emissive surfaces. Supporting evidence includes the pulse's infrared dominance, consistent with blackbody radiation from supercooled materials, though this model struggles to reconcile the rhythmic precision with chaotic quantum effects. A third interpretation from NASA's Goddard Space Flight Center considers gravitational lensing or space-time anomalies, where the object's path intersected a micro-wormhole or dark matter filament, refracting its emissions out of our observational plane. This accounts for the clean disappearance but requires invoking unverified physics, as no corresponding gravitational perturbations were detected in nearby planetary orbits. These theories, while anchored in rigorous analysis, underscore the event's resistance to unified explanation, with each framework accommodating portions of the data at the expense of others. The pulse's periodicity defies stochastic natural origins, yet the silence evades artificial intent without additional context. Collaborative efforts, including retasked missions from the James Webb Space Telescope, continue to scan the projected trajectory, but as of November 12, 2025, no reacquisition has occurred. Only sustained observation and potential future intercepts will discern which interpretation endures, if any, as the boundary of knowledge expands into this unresolved domain. Following the initial detection on October 17, 2025, the observation sequence unfolded with mechanical precision across a network of ground-based telescopes and orbital assets, each interval marked by the steady accumulation of data points against the vast backdrop of space. The object's approach had been tracked for weeks prior, its position plotted along a hyperbolic arc that carried it from the outer reaches inward, passing perihelion at 1.8 astronomical units, where solar heating might have triggered volatile releases, though none were observed. From that point, the trajectory reversed outward, accelerating under the sun's diminishing pull, with velocity measurements holding steady above 40 kilometers per second. This pace imposed strict windows for analysis. Every hour of delay widened the distance, dimming the object's faint glow against the cosmic background noise where starlight and zodiacal dust scattered faint reflections. The infrared pulses began shortly after perihelion passage, their rhythm aligning with the object's rotation period, estimated at 12 hours based on light curve variations, a cycle that repeated like a distant metronome in the emptiness. As days progressed, the sequence shifted from active emission to abrupt silence, the cutoff aligning with the object's recession beyond 2.7 astronomical units, where signal strength should have faded gradually rather than vanishing entirely. Subsequent sweeps by radio arrays and optical instruments filled the interim periods, their scans methodically gridding the projected path, but each pass returned only the quiet hum of baseline readings, empty spectra devoid of the expected thermal trail. These gaps in observation grew more consequential with distance. At 3 astronomical units, atmospheric interference on Earth-based systems compounded the challenge, forcing reliance on spaceborne platforms like the James Webb Space Telescope, whose cryogenically cooled mirrors could penetrate the chill of deep space, yet demanded precise pointing amid orbital constraints. The environment of observation itself evolved, from the crisp night air of Hawaiian mountaintops, where cooling fans whirred softly against the domed structure, to the sterile vacuum surrounding satellite arrays, where data relayed in packets across millions of kilometers, each transmission delayed by light's inexorable speed. Now, with the object estimated at over 3 astronomical units and receding further, the timeline compresses toward critical milestones that define the limits of human reach. Imminent retasking of deep space antennas aims to probe for any resumption of activity scheduled during alignment windows when Earth's rotation brings key facilities into line of sight, intervals shrinking as the angular separation narrows against the stellar field. What cannot be seen, the object's surface composition, its internal structure, or any subsurface mechanisms, looms larger in these pauses, the silence amplifying the scale of isolation, where light from the sun takes hours to arrive, diffusing into a pale illumination that barely warms the frozen exterior. Mission constraints tighten here. Fuel budgets for satellite maneuvers limit follow-up stares, and computational models strain to predict deviations without fresh inputs, their simulations running in endless loops on supercomputers, humming in climate-controlled rooms. The rhythm of waiting builds, each orbital cycle drawing the object closer to the heliopause boundary, beyond which solar influence yields to interstellar winds, a threshold where detection fades into impossibility. As observation intervals shorten, daily checks giving way to hourly vigils, the distance evokes a tangible pull, the vastness rendered in the faint delay of telemetry signals, the cold precision of coordinate grids overlaying star maps. Tension resides in this motion, the object's unrelenting outbound vector, carving through the Oort cloud's sparse veil, where cometary nuclei drift in eternal twilight. Environmental cues deepen the immersion, the gradual redshift in any lingering emissions, the expanding cone of uncertainty in positional fixes, the absolute quiet of vacuum unbroken by atmospheric whisper. Pacing accelerates toward the next pivotal scan, a convergence of assets poised to capture any irregularity, be it a fleeting burst or structural shift. In this progression, time itself feels weighted, compressing the expanse into a narrowing funnel where the boundary of the known presses against the unseen, hinting that continuity may fracture at any moment, revealing patterns long concealed in the dark. In the weeks following the signal's cessation, official channels adopted a posture of deliberate restraint, with NASA and the European Space Agency issuing only brief updates confined to trajectory confirmations and basic orbital parameters. Data dissemination, previously shared through open access repositories like the Minor Planet Center, shifted to restricted protocols, where raw telemetry required interagency approval before release, delaying publications by up to 72 hours. This measured caution stemmed from procedural guidelines established under international astronomy accords intended to prevent misinterpretation of incomplete datasets amid heightened public scrutiny. Conflicting analyses emerged from peripheral observatories. The Chinese Academy of Sciences reported faint microwave echoes along the projected path, interpreted as possible outgassing remnants, while the Indian Space Research Organization countered with optical data suggesting no such activity, attributing discrepancies to calibration variances across instruments. These divergences highlighted institutional silos, where access to full-spectrum readings varied, fostering restrained debates in closed forums rather than public resolutions. The consequences of this uncertainty extended into operational domains, with scientific teams enforcing procedural restraint to avoid premature conclusions that could skew funding allocations or mission priorities. Disagreements persisted on fundamental aspects, such as the object's mass estimates, ranging from 200 to 500,000 tons, based on gravitational microlensing effects observed during its inbound league, complicating models of its composition without a unified interpretation. Absence of a final framework amplified resource strains. Reallocation of telescope time from other surveys, like exoplanet hunts, proceeded under interim directives, while computational clusters processed petabytes of archival data in search of overlooked precursors. Indications of an impending shift accumulated gradually, with alignment windows for high-resolution scans narrowing as the object's recession velocity integrated over time, reducing viable observation periods from days to mere hours. Collaborative networks intensified monitoring, synchronizing assets across hemispheres to cover the expanding uncertainty ellipse, where positional errors now exceeded 10 arc minutes. As November 12, 2025 approached, the rhythm of updates compressed, with daily briefings yielding to real-time feeds from key facilities. Then, at 1427 UTC on that date, the Hubble Space Telescope, repositioned for a targeted stare, registered a reemergence of infrared emissions from coordinates matching 3I Atlas's extrapolated position, now at 3.4 astronomical units. The pulses resumed at the original 47.3-second interval, but with a modulated overlay in the visible spectrum, manifesting as low-amplitude flares, detectable only through adaptive optics. This development aligned with no prior model, introducing a structured variance that suggested adaptive behavior in response to the intervening silence. The narration pauses here, allowing the data's implications to settle without further elaboration. The reemergence of emissions from 3I Atlas, captured in the modulated flares, now spanning infrared and visible spectra, stands as a confirmed event within the observational record, its periodicity resuming with unaltered precision despite the intervening void. This resumption aligns with the object's calculated position, verified through cross-reference data from multiple space-based instruments. Yet the added spectral overlay introduces a layer of complexity that defies prior classifications of interstellar bodies. What remains speculative includes the mechanism behind the silence and subsequent adaptation, whether a response to external stimuli, an internal reconfiguration, or an artifact of unmodeled physics, each possibility constrained by the limits of current detection capabilities. The data, while robust in its raw form, resists integration into established frameworks where natural volatility would predict irregularity rather than this rhythmic consistency, and artificial origins invite interpretations that stretch beyond verifiable evidence. In this balance, science confronts its own perimeter, the known anchored in photometry and astrometry, the unknown expanding through the absence of explanatory models. Broader implications extend into the foundations of astronomical inquiry, where such anomalies challenge the assumption of a passive cosmos, one governed solely by predictable forces. Collective understanding shifts subtly here, as institutions recalibrate protocols for interstellar transients, incorporating enhanced monitoring thresholds and interdisciplinary reviews that blend astrophysics with information theory. The event underscores the fragility of observation itself, dependent on finite apertures, signal propagation delays, and the interpretive lens of human analysis, reminding practitioners that discovery often arrives not as illumination but as deepened shadow, prompting refinements in methodology without erasing inherent uncertainties. For science, this means an evolution in how anomalies are cataloged, no longer as outliers to be normalized, but as potential signals demanding sustained scrutiny, fostering a more adaptive posture toward the universe's vast, uncharted domains. Anticipated steps involve continued tracking along the object's outbound trajectory, with assets aligned for periodic sweeps that capture any further modulations, alongside archival cross-comparisons to identify precedents in historical datasets. Verification may emerge through advanced simulations that test adaptive hypotheses against observed parameters, or through collaborative arrays that extend detection baselines, gradually narrowing the cone of possibilities. Inevitably, this pursuit will persist, drawn forward by the object's recession into interstellar space, where each incremental distance tests the reach of instruments and the resilience of theories, sustaining a narrative that unfolds not toward conclusion, but through perpetual refinement, the cosmos yielding its truths in measured increments amid the enduring quiet.